All right, so here we are. We've worked our way up to this, naming the shape of molecules with one central atom and no octet rule exceptions. So what that means is even though we've seen expanded octets in the previous topic, we won't be dealing with any expanded octets for these, okay? But again, as a reminder, you know that atoms of elements in period 3 or and beyond can have an expanded octet, meaning they could have more than 8 electrons, either in bonds or lone pairs, around them if they are the central atom. So let's get started. Remember, in order to determine molecular geometry, the name of the molecular geometry, which describes the shape, the geometry, the shape of a molecule, we have to start with the Lewis structure. The Lewis structure is going to allow us to predict molecular geometry. Okay, so we've got phosgene here, and I need to determine how many, number one, how many valence electrons I have. Chlorine has 7 times 2 is 14. Oxygen is 6, which is 20. Carbon is 4, which is 24. I did that in my head because we've had plenty of practice there. Okay, so I have 24 valence electrons to work with. Next step, what is my central atom? It's never hydrogen. It's never fluorine. We are looking for the least electronegative element to be our central atom. Here it is, carbon. Okay, so place my carbon here. Place oxygen, and let's put our chlorines here. Don't worry about how you place them, whether it's at an angle, slanted, or you may want to put one chlorine here and one down here, straight above and below. That is fine. I'm just going to place it like this out of habit there. All right. So we have to start with at least a single bond between all of the atoms here. Next step, fulfill the octet of all of the atoms around the central atom. So 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Let's count and see where we are. Remember we had 24 to begin with to place. I've got 2, 2, and 2 here. 2, 4, 6. Those have to be there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, I'm done, right? Uh-oh. If you look at your central atom, it does not have an octet. Now, we know that there are some central atoms that can violate the octet rule. They can have less than an octet. Some examples are beryllium, boron, aluminum. Carbon is not one of those. And again, they told us that these were going to be no octet rule. We're going to have no octet rule exceptions. Surely ALEKS didn't lie to us. So what do we do? Well, if you run out of electrons, we've run out of valence electrons, and I need still 2 more to satisfy this carbon. When you run out of electrons to place, what that means is you need to start introducing double or triple bonds. Okay? So I've run out of electrons. What can I do? I can take 2 electrons here from this lone pair, and they can be placed here, making that a double bond. Well, let's recount. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All of my atoms have an octet. Octet here, octet here, octet here, and the central atom is also satisfied with an octet. Now, when some of you all were doing this, I do want to show you why the most probable Lewis structure is this one and not this one. Okay, this is where our discussion of formal charges would come into play at. And when you're trying to determine formal charge, I'm just going to add this additional information here. The way you find formal charge is you take the number of valence electrons that the atom came in with and you subtract from it the number of electrons that are assigned to it. So for example, how many valence electrons does an atom of chlorine have? 7, right? How many electrons are assigned to this chlorine atom? Well, these lone pairs are his or hers, but it can only get 1 electron from this pair because these are being shared. So it would have 1, 2, 3, 4, 5, 6, 7 electrons assigned to it. So that would give this a formal charge of 0. For this oxygen atom here, it has 1, 2, 3, 4, 5, 6, and then you only count 1 electron from a single bond, 7. Okay? So oxygen came in with 6 valence electrons. It has 7 assigned to it, so its formal charge is -1. Here, this chlorine atom has 7 valence electrons, but assigned to it, it has 1, 2, 3, 4. For a double bond, you count 2 because there are 1, 2, 3, 4, so it gets half of that. So 1, 2, 3, 4, 5, 6 electrons assigned to it for a formal charge of +1. This carbon atom here, 1, 2, 3, 4. So 4 for valence electrons minus the number assigned is 0. Okay? So let's compare this. Some of y'all may have got that when you tried to draw your Lewis structure to this. What's the difference? Well, here the formal charge of this carbon atom is 0, of course. The formal charge of this chlorine here, 1, 2, 3, 4, 5, 6, 7 assigned, and 7 valence electrons, so 7 minus 7 is 0. 0. For this one, 7 minus 7 is 0. Valence electrons minus assigned. For this one, oxygen has 6 valence electrons assigned to it. It has 1, 2, 3, 4, and you count 2 for a double bond. 5, 6. 6 minus 6 is 0. The reason why this is the most probable Lewis structure is because the formal charges are minimized. You want to go with the option that has the formal charges minimized as much as possible. In this case, all the formal charges are 0. In this case, I've got the formal charge of this carbon and this chlorine is 0, but this oxygen has a formal charge of -1, and this chlorine has a formal charge of +1. It makes less sense than this one. Not to mention, if this double bond were to form here, that would mean that this carbon pulled electrons away from chlorine, and chlorine is much more electronegative. So this is the Lewis structure that we are going with. And so in order to determine molecular geometry, number 1, we get the Lewis structure. Number 2, let's figure out what the electron domain geometry is. And from that, we can pick the correct molecular geometry using the ALEKS notation. So what is the ALEKS notation of this, of phosgene? Well, it is AX3. And are there any lone pairs of electrons around the carbon atom? No. So I will put the E here. Let's put a 0 there. And really, if we're going to write this to be complete, we just put AX3. Okay? So let's refer to our chart here. That makes it very easy for us. We have our Lewis structure. Let's determine the electron domain geometry. How many electron domains? 1. Even if that's a double, it doesn't matter if it's a triple bond. It only counts as 1 electron domain. 2. 3 electron domains. Number of electron domains, 3. The electron domain geometry is trigonal planar. What is the molecular geometry? So what this is telling us is for molecules that have an electron domain geometry that is trigonal planar, the molecular geometry could be either trigonal planar or bent, depending on whether there are lone pairs or not. So the thing about molecular geometry, and listen to me very carefully here, is that molecular geometry only depends on the position bond angles of the atoms, not the lone pairs. Okay? We're only looking at the positioning of the atoms. So in this case, if I'm looking at the ALEKS notation, this tells me that there are 0 lone pairs here around the central atom. It's AX3. So our electron domain geometry is trigonal planar. There are no lone pairs. There are 1, 2, 3 atoms around the central atom with no lone pairs. So the molecular geometry is trigonal planar.